So let's get started. Ready? 1, 2, 3, go. Okay. So we're just going to pick up where we left off last time with Bayesian methods. Same announcements about project teams and homework 4, but more urgently, if you didn't get Rahul's email or Piazza post about the Google presentations from homework 3, make sure you take care of that as soon as possible. Make it public if possible. If you can't have access to do that, which was happening with some people with Harvard emails, then share access with the staff email list, which is staff@cs109.org, and see Rahul's Piazza post for more on that. And make sure you do that soon, otherwise we can't grade the presentations if we don't actually have access to it for that. Okay, and hopefully you're working on your project teams and the next homework, and we're just going to pick up where we left off. Bayesian methods. Okay, I'll start with a really simple, it's not worthy of the name puzzle. I don't know what it's not worthy of the name problem. Which proportion is bigger, 1 out of 2 or 40 out of 100? Okay, 1 out of 2 is a bigger proportion than 40 out of 100. Why am I asking this? Well, you know, as fractions, 0.5 is greater than 0.4. That's not very controversial. However, there's no context here. So let's look at the same numbers, but in a specific context. Suppose you are comparing 2 baseball players, and this is the data you have on the 2 players. Player A, you'll only have a very small sample size. You've seen that this baseball player at A at bat twice got 1 hit, right? So 1 out of 2. And then the other baseball player, player B, you have a lot more data. You have 100 at-bats, and player B got a hit 40 times out of 100. Which player would you rather have on your team, just based on this information? B. Why? I trust the numbers a lot, probably a lot more. Okay, would anyone prefer A? Just based on this. But, you know, 0.5 is greater than 0.4. But what you did, you know, in your mind was you did your own little Bayesian calculation implicitly. And you adjusted for the sample size, and you kind of were saying, well, sample size of 2 is pathetically small, and we have a lot of uncertainty there. So you're kind of doing your own little implicit statistical calculation. Okay, next question. Let's say it's a cab driver or Uber, and you get the data on their reliability. Now, the first driver, you're aware of 2 trips he made, and he only reached the destination 1 out of 2 times. That's not very good. But the second driver reached the destination 40 out of 100 times. The other 60, I don't know, either he got lost or he got in an accident or something like that. Okay, which driver would you prefer if you had to choose one of these 2? Neither. I said you have to choose one of the 2. You're stranded somewhere. You don't have your own car. A. I would prefer A, because if 1 out of 2, again, you know, 2 is a very, very small sample. So it could be that, you know, one time his car broke down and the other time it was fine. But driver B, you know, 40 out of 100 times success, that's a 60% failure rate for taking a cab. That is really, really, really bad, okay? So hopefully you can see the point here. The numbers are the same in each of these, but the context changes, and how you would react to this, what decision you would make, and how you would interpret these numbers completely depends on the context. And so, you know, I think people naturally think like Bayesians here, in the sense that you have some prior, if you know even a little bit about baseball, you know that getting, you know, 40% batting average is extremely good. If you know anything about cab drivers, you know, 40% success rate is horrible for going in a cab. Okay, so you have some prior in your mind, and if you have a large sample size, you don't need the prior that much. Those numbers seem pretty reliable. But with a small sample size, you rely more on the prior. So we didn't go through a lot of math, but I wrote down a couple equations, or I had a couple equations on the slides last time, for the beta and the binomial and the normal and the normal. So if you have a normal distribution and a normal prior, or a binomial distribution and a beta prior. And in both cases, so those are probably the two most famous, widely used Bayesian models. There's a lot of other models too. But in both of those cases, as well as a lot of other Bayesian models, what you see is that your best estimate for the thing you're trying to estimate, in this case, you really would want to know, what is the true success rate of these baseball players or these cab drivers if you had an infinite amount of data. And you never have an infinite amount of data, but hypothetically, if you had an infinite amount of data, what would the true proportions be? Okay, and your best estimate is always going to be a compromise between your prior beliefs and what came from the data. And in those cases that I mentioned, the beta binomial and the normal, and a lot of other nice cases, it's actually a weighted average, where the weights, so you put some weight on the prior and some weight on the data. The larger the sample size, the more weight you put on the data, right? And the stronger, more sure you are about your prior knowledge, then you put more weight on that. So it's this trade-off between, how sure are you? Like, do you feel like you know nothing about baseball players? Or do you feel like you have a pretty good understanding of how baseball players or cab drivers behave? But even if you know very little about baseball and very little about cab drivers, I think almost anyone would prefer player B but driver A, just based on this information. So that means when people say they have no prior information, that's usually kind of an exaggeration. Usually at least you know a little bit. You may not know how to quantify it. You may not have a lot of confidence if you don't know much about these subjects, but at least you know what values would be ridiculously implausible, that kind of thing. Okay, so it's just a simple example illustrating that a lot of times we implicitly are using priors, and the Bayesian calculations is just an explicit quantitative way to do this kind of informal reasoning. So just a more rigorous version of simple examples like that. So this is, I mentioned this example briefly in a previous lecture when we were talking about regression and regression towards the mean. It's a very famous, very instructive example due to Efron and Morris. So they were looking at baseball players, and they were illustrating the importance of shrinkage estimation. And this is a different picture of something I showed earlier. So what they did is they took 18 baseball players and they looked at the first 45 at-bats for the season, and then they applied these kind of James Stein shrinkage ideas. So that's called the JS estimator. JS is James Stein. And just kind of qualitatively, you can see here that the original, so on the left, you see that they're all over the map in terms of their batting averages based on the first 45 at-bats. And then the James Stein is shrinking them all towards the mean, okay? So it's doing regression toward the mean for you. It's shrinkage towards the grand mean. Grand mean is the overall, if you average all of those players and come up with one overall mean, and then you shrink towards that. And this is the first, I think, applied example of what's called empirical Bayes. So I mentioned some of these controversies over the subjectivity of Bayes, like where does your prior come from? Is the prior just your subjective belief? And a lot of people who might benefit from using Bayesian methods but are uncomfortable doing so because of this inherent subjectivity. Okay, so empirical Bayes is a way to try to make that more objective, where you are actually estimating the prior using the data. So in this case, instead of having some prior mean that you knew in advance, you're estimating the prior mean that is kind of the overall batting average using the data. And for this example, they did it actually, when they did the James Stein or empirical Bayes type calculation, it actually did better than the naive thing. The naive thing is just, if you got 5 out of 45 hits, then your estimate would be that your probability of a hit is 5 out of 45. And that would also be the MLE, maximum likelihood estimator. Okay, but it doesn't work nearly as well as applying the shrinkage estimation. So they actually did better with 16 out of the 18 players. And usually when you're, analyze real data, you don't actually know what the truth is, but they kind of designed this analysis in a clever way where they just looked at the beginning of the season, and then the rest of the season was very long compared to just the first 45 at-bats. So they had a reasonably large sample size for these players, so, essentially know the truth. Okay, so just to go into a little more detail about this, I gave a URL here that I took this picture and the next couple of pictures from because I like the way he presented it. This varianceexplained.org is a blog by David Robinson, who was actually a stat concentrator at Harvard. He was a stat concentrator when we had 1 or 2 per year. It's around the time when I first came here. So the concentration has been growing a lot. And now he got his PhD recently, and he's now a data scientist at Stack Exchange. So I recommend his blog. It's in R, but don't hold that against him. R and Python are both good, both useful. Okay, so he just took this baseball example and was just kind of showing in more detail what's going on. So this is a histogram for, so he got a baseball data set, and it's a public data set on baseball players. So he gave the details here at the blog post about how to get that data. So it's a data set of baseball players, and this is the overall distribution for all the baseball players, okay? And so he's using the data to estimate the prior. That's called empirical Bayes. That used to be somewhat controversial. There used to be Bayesians who were very upset about empirical Bayes because in a strict philosophical point of view, you're not supposed to use your data your prior shouldn't depend on your data. It's supposed to be that your prior is separate from the data, and then you put in your data. So there have been some controversies, but I think those controversies have died down, and it's now pretty accepted as basically an approximate way to do, to come up with a reasonable prior. And it's closely related to hierarchical models, and so it's less controversial now. But it makes, good intuitive sense that if you don't have actual prior data, that is, it could be that you just, took the last 3 years of baseball player data and then looking at the current year as a separate thing. But if you just have this one data set, and let's just try to come up with one overall distribution to represent batting averages. Okay, so as I was describing last time, the natural choice, if you're talking about baseball players and either you get a hit or you don't, it's natural to model that as a binomial. Success is a hit, failure is not getting a hit. So if we have binomial data, for each baseball player, we have a binomial random variable. By far the nicest choice of prior is going to be a beta. So here he just estimated, he just chose a beta that fits the overall distribution as well as possible, and it turned out to be beta 79, 225. And there's several ways that you could choose which beta are you going to use. You could do maximum likelihood, but you could also just do a more quick and dirty method like figure out what's the mean and what's the standard deviation of that distribution, and then find a beta that matches the mean and matches the standard deviation. And that might not be quite as good as maximum likelihood, but it's probably perfectly fine for this type of thing. So you can see it's not a perfect fit, but it looks pretty reasonable. So that's the beta distribution that he used. And then once you have that, you can not only can you give point estimates, like you can adjust. So, if you had a baseball player who had, only a very small sample size, small number of at-bats, the prior is going to be really important for estimating the batting average. But it's not just point estimation, right? It's not just saying, I'm going to estimate that this player's batting average is, 0.29, okay? You get a whole distribution, so that is for each baseball player. This is just listing a few of them, and for each, the dashed line is the prior, and then the colorful ones are the posteriors for each of several different baseball players. And you notice that they are sharply peaked because for these players you actually do have plenty of data. And the prior won't matter much, right? The prior is only going to make a difference if you have very little data. Okay, so the nice thing is that for each of these players, you have the entire posterior distribution. Okay, so you can answer basically anything you want to know. You know, if you want to ask a question like, what's the probability that this player's true batting average is between 0.37 and 0.39? You can just read all of that off of the posterior distributions, right? You can find, you know, the posterior mean is just the mean of the posterior distribution. You can find the posterior median. You can find intervals. You can answer all kinds of questions without needing to come up with a different method every time you want to ask a different question. You just read the information off of the posterior. So that's very, very useful. And just to see, like, if you were super naive about this and didn't actually do, you know, anything, and you're just using maximum likelihood, and look through your data set and figure out and try to rank players. So who are the best players? Well, this is who you'd get at the top of your list. These are H is hits, A, B is at-bats, and sorry, the column headings got a little misformatted for some reason. So these players, it's 1 out of 1, 1 out of 1, 2 out of 2. So you're just ranking the data set, and this is what you would get, because it's going to find some people who had a tiny sample size and, you know, 100% success rate. That's completely useless. And then if you apply the empirical Bayes, so the empirical Bayes estimator, this is just listing the top players in this particular data set. These top players all have sample sizes in the thousands, because people with very small sample sizes, they're just going to be shrunk to the mean. Okay, so they're just going to look average. And I don't think this is very controversial for baseball players, but recently I did read about some very, very bitter controversies about this kind of thing with hospitals. So, you know, there's a lot of interest in ranking hospitals, you know, which hospital is the best and things like that, and that really affects their funding and who goes to which hospital and things like that. But different hospitals have different sample sizes, right? You have small hospitals, large hospitals, hospitals that perform hundreds of procedures, and some that don't do so many, okay? So from a statistical point of view, you do want to do something that accounts for regression toward the mean. You do want something that, you know, it's kind of Bayesian shrinkage estimation. But then the controversy comes from the fact that you could have a hospital that, you know, performs a certain surgery and they have 100% success rate, okay? And then this says, sorry, you get shrunk down to the mean. And they're very, very upset, right? Because it's like, they couldn't have done anything better. They're 100% successful, but, you know, sample size not big enough. So, you know, you can get into some tricky policy issues with that statistically speaking, we do expect regression toward the mean to occur. We do have prior information. So, you know, if for that one hospital you don't have that much data, it makes sense to construct a prior based on all the hospitals, okay? But then an individual hospital might be very upset that you're using worse hospitals than them to adjust their numbers, right? So that's we talked about this a little bit with the James Stein stuff too. You're estimating stuff for one baseball player or one hospital based on other independent baseball players or hospitals, which might be considered unfair, but statistically it's a better thing to do, at least in terms of your overall. And you might do, you know, better for some hospitals and worse for others compared to just doing something more naive. But overall, you're probably going to do much better. Like in this baseball example, Efron and Morris did better for 16 out of the 18 baseball players. And if you also look at the overall total squared error loss, it was like a factor of 3 improvement. So it was a massive improvement over just using plain maximum likelihood estimation. Okay, and I like what David wrote on this. We hired a data scientist to analyze our big data, and all we got was this lousy line of code. So it's so simple. It's just one line of code here that what was going on here is instead of looking at successes out of total, he just added 78.7 in the numerator and 303.5 in the denominator. And the reason for that is what I was discussing last time about the beta and the binomial. Remember I said in the posterior distribution for the beta, you just add the number of successes to the first parameter, add the number of failures to the second parameter, okay? So that's effectively creating a pseudo count. The pseudo count is saying, give every player 78.7 hits and assume that they have an extra number of failures of what it was, the other parameter was like 225, and the total is 303.5. So it's like effectively giving everyone that amount of information from the prior. And so it's a very, very simple. We're going to get to some, much more complicated Bayesian problems, but already this simple kind of beta and binomial and the normal and the normal are already quite useful for a variety of problems. So the reason that this formula is so simple is because we used a conjugate prior. The beta is the conjugate prior for the binomial, and that means that it's incredibly easy to do these updates. Sometimes you're working on more complicated problems where the conjugate prior doesn't seem to make sense to you in that case, and you need much fancier computational methods. But for problems where it seems reasonable, like the beta seemed like a good fit. So the next extension of this might be, what have you noticed if you studied the data a little more, or if you had a little more background knowledge about baseball and you know that pitchers tend to be the worst hitters, right? Pitchers are usually not good hitters. And then you might want to consider like a mixture model where you say, some people are pitchers and some are not, and you might, can have separate priors for those, and you could delve further into the data. So you might think that having that overall unimodal prior distribution, well, it looked reasonable in this case, but in other cases, maybe there's two peaks and you need a fancier prior and things like that. You might need fancier methods. But here, even this simple thing seems to work pretty well. All right, so as I mentioned, for any player, this is the posterior distribution for Derek Jeter. And see that interval in red at the bottom? This is just a simple picture illustrating the idea of credible interval, which I described a little bit last time. So credible interval, I don't even like the term that much because I would just call it a probability interval or posterior interval. So if I want to say that I'm 95%, I want to give 95% probability to Derek Jeter's batting average being between something and something, all I have to do is just pick out 95% of the area under that density, and then that's the interval. And there's not a unique way to do that. There's two standard ways to construct such an interval. One is to try to make the interval of smallest width as possible. So what that would correspond to is, imagine it would be great if I had a stick, but I can't reach that high anyway. You had a stick at the very top of that distribution and then push it, or just, if it were on a piece of paper, use a pencil. Put the pencil at the very top and then push it down further and further. The point being that you're trying to get the stuff of highest density, right? So pick the points on the horizontal axis that have the highest density. And that way you're going to accrue more and more probability as easily as possible and try to get an interval of the smallest possible width. That's one approach. Another simpler one is what I mentioned last time, just cut off 2.5% at each end. Of course, 95% is arbitrary, but that's pretty standard. People like to have 95% intervals a lot of time. Okay, so I'm just saying pick out 95% of the area just by cutting off 2.5% of the area on each side. Okay, and for the beta distribution, it's easy to do that kind of calculation. And if you had a posterior distribution, as long as you can calculate area under the curve, which is not usually very hard to do, either numerically or analytically, then you can construct this interval. All right, so I wanted to this gets confused with confidence intervals all the time. So I wanted to make sure that the contrast between a confidence interval and a credible interval is clear. In a course like Stat 100 or typical intro statistics or high school statistics courses, they only talk about confidence intervals, not credible intervals. And a confidence interval, by definition, It's in the frequentist paradigm where you're thinking of the parameter theta as fixed but unknown, okay? And you're coming up with an interval from, let's say, from A to B, and you're hoping it has 95% probability of containing theta. The problem, though, is that, of course, that interval is constructed from the data. So the endpoints A and B are both functions of y. So y is the data, theta is the parameter. So the parameter is fixed in the frequentist setting. The data is random. The problem here is that this is a random interval. So if you got theta is fixed, but the interval is random. And people have a lot of trouble interpreting that correctly. And I think it's fair to say that most people, even the word confidence, it suggests, okay, suppose you have your data and you computed your confidence interval, and suppose you got the interval from 3 to 7, okay? The very word confidence, it's suggesting that we should be 95% confident that theta is between 3 and 7, okay? That's what it sounds like. And that's how people think of it. Like, okay, I can be 90, you can find people everywhere, you know, including in good scientific journals or in courses or wherever, where basically that's what they say. We can be 95% sure that theta is between 3 and 7. But that's wrong. That doesn't even make sense. Because in this frequentist paradigm, theta is a constant. The probability that theta is between 3 and 7, it's either 0 or 1, right? Because that's just a deterministic statement. Either theta is between 3 and 7, or it isn't, okay? We don't know which one, but it's either 0 or 1. It's like saying, what's the probability that 2 plus 2 equals 4? That's 1, okay? It's exactly like that, except imagine it's some computation that we don't actually know the answer. So it's 0 or 1, but we don't know which. But that's pretty problematic, because you want to be 95% sure that you've captured the truth, but that's not the interpretation. The interpretation is repeated sampling. So if you repeated this procedure over and over and over again, and you don't just have one interval, you have, say, 1,000 intervals, and then it's saying that, you know, in the long run, about 95% of those intervals will contain the true theta, okay? So if you did the experiment over and over again, so it's all about hypothetical repeated sampling. A Bayesian wants to focus on the data at hand. The Bayesian says, here's our data set. We want to be 95% sure that we have the, you know, an interval that contains the truth. Okay, frequentist, you can't actually even say what the probability is that you, in your data set and your interval, that you contain the truth. Okay? So the interpretation is completely different. In some cases, a frequentist confidence interval could even return the empty set, right? I've seen this happen, okay? No one would actually go on and report the empty set as their confidence interval, right? Empty set, that is nothing, okay? But that's actually possible. For example, I mean, this is an extreme, stupid example that no one would actually do. But if you construct your interval by saying, with probability 0.95, I'm going to do minus infinity to infinity, and with probability 0.05, I'm going to do the empty set, that satisfies that definition of a confidence interval, right? 95% of the time it's going to contain the truth. The other 5% of the time, empty set, it failed, but that's okay, you're allowed to fail 5% of the time. Okay. So you can get examples like that where you get something that's completely impossible and it doesn't violate the definition because definition refers to repeated sampling. All right, so now let's contrast that with credible intervals. In the credible interval, it looks similar, but the interpretation is completely different because I wrote it as a conditional probability, so it's given y. So the Bayesian says, let's condition on the data because the data is what we actually know, right? So we're going to fix the data, we're going to condition on that because that's what we've observed, and we're going to treat the parameter theta as random because we want to quantify our uncertainty about the unknown. Okay, so then we have, you know, a conditional statement. Given the data, there's 95%, this is why I also just call it a probability interval, not just a credible interval. Given the data, there's a 95% chance that the interval we constructed will contain theta, okay? So it's a much more straightforward interpretation. It's just saying 95% posterior probability for the actual data set we have, not hypothetical data sets that we don't have. Okay, so that's the difference. So the interpretations are completely different. But on the other hand, even though the interpretations are different, that doesn't actually mean that you can't have the best of both worlds. Because at the end of the day, an interval is just an interval, right? And both of these methods or approaches are referring to interval estimation. So rather than just estimating one number summary, we're trying to give an interval. Well, both of these are giving an interval. So you could say, that's called the coverage problem. If you take an interval estimation procedure and look at the probability that it contains the true value, that's called the coverage probability. There's no reason you can't construct a credible interval using a Bayesian procedure and then assess its frequentist performance, right? There's nothing stopping you from doing it. People don't usually do it because they're too lazy, but there's nothing actually stopping you from doing that. So this goes back to what I was saying earlier about the fact that there's no inherent conflict between Bayesians and frequentists, or that there shouldn't be. Because Bayesian models, it's a very powerful way to construct procedures. And then if you're interested in the long-run performance of that procedure under repeated sampling, then you can investigate that, either mathematically or through simulations. So you could imagine, you know, we have this way of constructing a credible interval, and then you could say, okay, now I'm going to fix theta, and I'm going to apply this procedure many times in a simulation and see, is it true that 95% of the time it does contain the truth in the frequentist sense? And usually it works pretty well. So usually the Bayesian methods will be pretty good from a frequentist standpoint as well. It's not going to be exactly 95% usually because it's not designed for that. And you can make up examples where you will get, you know, the confidence interval and the credible interval will be very different. So there are always going to be weird examples where you get different answers, and it's fun to think about those examples. But in most normal, everyday problems that you would want to deal with, if you do a Bayesian method, get a credible interval, if your prior is not ridiculously dogmatic, it's going to have good frequentist properties too. So you don't have to choose one or the other. Okay, so this was an example from David Robinson's blog again. It's just showing visually a bunch of confidence intervals, which are in orange, and credible intervals, which are in blue for baseball players. And you notice the ones, these are ordered from top to bottom, it's increasing sample size, so increasing number of at-bats. And so you can see at the top, there are huge differences between them, where the confidence intervals are much wider because like that one at the top, that's a baseball player who only had 3 at-bats, and so, you know, the confidence interval stretches almost all the way from 0 to 1, okay? Because it's not using prior information. That actual real baseball players are not going to vary that much in their batting averages, okay? So the credible interval is much narrower because we actually do have good prior information in this case. But then when you go down to the players with large sample sizes, then there's very little difference anymore. So for small sample size, there's a big difference, and the Bayesian approach is probably better if you have a reasonable prior. For a large sample size, anything reasonable is going to work anyway. Which is great, because if these two procedures, you know, give you intervals that look the same, first of all, you have a lot more confidence that it makes sense, and secondly, you can enjoy both interpretations. Both interpretations of the interval now make sense, instead of having to be really careful about, you know, to avoid misinterpretations. So, yeah, that's in practice, that's one of the biggest statistical errors, is misinterpreting what confidence intervals mean, because we want it to be a credible interval, but then usually it was calculated without actually doing the Bayesian thing, and it's not. All right, so here's another example. This is called the multi-armed Bandit problem. And I took this example from the Probabilistic Programming and Bayesian Methods for Hackers book that I mentioned last time. So there's IPython notebooks for all of these calculations. So it's a nice example to run through, and then you can look at those notebooks if you're interested. So this is a very old, classic, famous problem in statistics where the reason it's called the multi-armed bandit is that you imagine that you have a large number of slot machines. So this could be in Las Vegas, although you don't usually see octopuses there. But they picked an octopus because you're imagining like you have to choose between all these slot machines, and maybe the octopus can do 8 at one time, but a person has to choose 1. So imagine you have all these slot machines lined up, and the slot machines have different properties, okay? Each slot machine, you know, you pull the lever, and then maybe it gives you nothing, maybe it gives you a reward, maybe it gives you a small reward, maybe it gives you a huge reward, right? So assume that all of these different slot machines, they all have their own unknown probability distributions for what kind of rewards it gives you. So you just got to the casino, you see like, you know, however many n slot machines lined up, you have no idea which one has better payoffs. Okay, that each has its own properties, okay? So, and you can only do one at a time. So you pick a slot machine, pull the lever, and you know, you get some reward, hopefully, and then you could either use the same one again, or you could try a different one, and you know, how would you even decide in what order do you want to try out these slot machines? And you know, how would you define optimality and then find an optimal algorithm? There's a huge literature on this problem. Tons of very difficult math has been created to try to solve this type of problem. And it's, you know, considered a very, very difficult problem. And so I wanted to show you, or in this example, the author here came up with a very, very simple algorithm. That I can describe this algorithm in 1 minute. It's, you know, you can program it very easily, and it's not optimal in any particular mathematical sense, but it works quite well. So through Bayesian thinking, you can come up with methods, you know, without needing some like incredible feats of mathematical problem solving. You can come up with a reasonable algorithm that's going to work quite well in practice, and you can implement it quite easily. So the main reason that this problem is so challenging is what's called the exploitation trade-off. And what that means is, ideally, if you knew which slot machine was the best, and assuming that's not changing over time, then go to the best one and then keep doing that one over and over again, right? But you have no idea which one is the best. So if you could afford to do this, you might say, well, I'm going to pull the lever on each of these slot machines 10,000 times each and try to estimate which one is the best one, and then I'll just start doing that one over and over. So that's the exploration part, right? Exploration means you're trying out different slot machines. Exploitation means you found a really good one, and you want to mine it for all you can. But the problem is you don't have the luxury of being able to do in advance this huge study of, you know, like 1 million, you know, get a sample size of 1 million or something to try to figure out which one is the best. So you want to learn which one is the best, but at the same time as you're doing that learning, you also want to maximize your rewards along the way, because you're only going to, you know, be there for 1 hour or something, right? So you have limited time and resources, so you need to kind of simultaneously do these things. So we're going to have a guest lecture on A/B testing later in the semester, which many tech companies are doing these days, where, you know, you do randomized experiments between different treatments. For example, different styles of ad or different website designs to try to, you know, maximize the number of people who sign up or purchase your product or things like that. And this is kind of has that flavor of you know, doing an experiment, except that where you know, you're trying out the different slot machines would correspond to if you're a tech company and you're trying out showing different pictures of the product you're trying to sell or things like that. But you can't afford, you know, your company can't afford to just like spend years doing experiments and find the optimal things. You're also trying to make money in the short run too. So this is kind of like, trying to learn as you go along. So there's that trade-off. Okay, so here's a very simple Bayesian method for this. We start with a prior for each bandit. So that's just a prior distribution saying, maybe there's a 30% chance that it will give me nothing, and there's a 20% chance it will give me $1, and there, just some distribution for how much the payoffs would be. We always have that issue of how do we choose the prior, but you try to choose something reasonable, not too extreme. Maybe you have some actual prior information of slot machines. Maybe you've been to Las Vegas before or whatever. It's a very general context, right? It doesn't actually have to be about gambling. Maybe you have some real prior information just based on your experience, or maybe you just do something that doesn't seem too extreme, okay? And then you sample from the prior for each bandit. So they're called bandits just for historical reasons. The bandits are the slot machines, okay? So you sample from the prior for each of those, and you can think of that as just being like, simulating a value for what that slot machine might give you as the reward, and then pick the largest one and choose that one, and you pull that lever, and then you got more data from that bandit, and you update, right? And then you keep doing that, okay? So in other words, don't just choose the one that you think has the largest expectation, because then you would just keep choosing that one, right? It's more randomizing more than that by simulating random values from the prior. Okay, so simulate from the prior, you get data on that slot machine, you update the prior, and that's just like what we were doing with the beta binomial or the normal. You update your prior, that becomes your posterior becomes the new prior, and then you just keep repeating that. So very simple to code this up, and this was his simulation results. So in this example, he assumed that there's 3 slot machines. So that's why there's 3 different distributions being shown here. And start with, this is for a simple case where it's, either it gives you a prize or no prize, okay? So it's yes or no, you get a prize, and you want to maximize the number of prizes you get. Okay, so up on the upper left is the posterior after 1 pull. So you've just pulled, one of the 3 slot machines, and I think you just started with flat priors here, okay? Just assuming, I have no idea what, it could be anywhere between 0 and 1 as the probability with equal probability, so uniform distribution, in other words. Uniform distribution is beta 1, 1, by the way, so it does fit into that context. Okay, but then after pulling one of the slot machine levers, then you got data, at least for that machine. Okay, so that's after 1 pull, and then after 2 and 5 and 15 and so on. And what you can see here in these plots is that and I should mention that the vertical dashed lines are the true values, okay? So the red one is the worst. That you can see, the true value is like 0.6 for that one, and 0.7 something for the purple one, and 0.8 something for the blue one. So the blue one is the best, all right? So, okay, so you keep doing this, let's say 1,000 times here, and you'll notice, first of all, that these distributions are, at least the purple and at least the blue one is really, really good there, okay? So for the blue one after 1,000 pulls, it's a very, very sharp peak centered at the true value. The other ones, they're sort of close to the truth. They're not nearly as good as the blue one. That's because you have less data. The reason you have less data on those is that it's trying to do this exploitation thing. So it's collecting, it noticed early on that the blue one is better, but it's not completely sure, right? It could just be that just by chance it appeared to be better. But it looks like the blue one is better. And so it was using the blue one more than the other ones, and so it got a larger sample size. So if you keep doing this, it will gradually, all of these distributions are going to get more and more sharply peaked around the truths. And that doesn't depend much on the prior. So you could change that prior there and do it something else like this, and it's going to look quite similar in the end to this, as long as your sample sizes are reasonable. Okay? So again, there's just, a very, very quick, there was very little math there, right? It's just a simple algorithm that you could come up with in 5 minutes, and you could program it pretty easily, and then you can try it out. And you don't need to prove any hard theorems about this. And, the prior is going to wash away as you get more and more data. Okay. So here's a famous example from the Bayesian data analysis book that I mentioned in the last lecture. That's the book for Stat 220 and the leading Bayesian textbook. So this is a map of the, what's shown in black here are the counties in the US that the highest 10% in terms of kidney cancer death rates. And there's some age adjustment built into this that I won't worry about just because some states have different age distributions than other states, and it kind of adjusted for that. But that's not really the point. Okay, so what do you observe about this map? Which parts of the country would look worse and better? Black is bad. The black dots there are the counties that have top 10% of kidney cancer. Well, California looks pretty nice, which is good. I'm from California. What kind of trends do you see? Low population density. Okay, so you see that, let me overlay this with let me show also the lowest. Okay, so you see, yeah, so I mean, it's, Midwest and well, basically mostly coastal areas and more urban areas you see less. So does that mean it's dangerous to live in rural areas, that it's going to put you at risk for kidney cancer? Well, no. As you said, we also have to take into account the population densities. And so here we also show the lowest kidney cancer death rates. So that the upper map is the highest, the counties with the highest rates, and then the bottom one is the lowest. And it doesn't look too different. It would be actually pretty hard to distinguish. I mean, there's randomness in here, but there's no obvious way to even know which is which. And here they are on one map. This is from an article I really like by Howard Weiner called The Most Dangerous Equation. So that article is about examples where not thinking about sample size, just like applying an equation or a calculation without adjusting for sample size can lead to huge mistakes. So the blue ones are the lowest rates, and the counties with the lowest rates, and the orange ones have the highest rates, and they're actually not too different. Okay, so that doesn't take into account sample size, right? So if you have a county that has a million people, and if there's always going to be random fluctuations, right? If a few more people have kidney cancer, or a few fewer have kidney cancer, and there's a million people, that's completely negligible. But what if you're talking about a tiny county that has 100 people, right? You have a county with 100 people, and it might be that none of them have kidney cancer, then the rate is 0, okay? And maybe just by bad luck, maybe 2 of them do, and then suddenly it's 2%, which just would be terrible. So it doesn't adjust for any of that, like the baseball example. It doesn't take into account sample size. So here's a simple model. I'm not going to go into all the mathematical details of this, but I just want to show you the outline of the model. So a Poisson would be a natural model. We have talked about the Poisson distribution. A Poisson would be a natural model to use for the number of people with a certain rare disease in some county. Because remember, the Poisson makes sense if you have a large number of trials and each one of them is a rare, right? A large number of things that can happen, but each one of them is rare. Okay, so if there's a lot of people, but each person is unlikely to get kidney cancer, hopefully, then a Poisson is going to be a pretty reasonable model. And of course, Poisson, and then with some unknown parameter, and it also has an NJ there to reflect the sample size. So we would expect, to be Yj is a model for the number of people in the jth county who have kidney cancer. Of course, it's going to depend on Nj is the number of people in that county. The 10 is just an adjustment because they're looking at per 10,000 people or something like that. And so for the Poisson, it turns out that the conjugate prior is what's called gamma, and we haven't talked about the gamma distribution, and I'm not going to worry about the mathematical details of the gamma right now. It's a generalization of the exponential distribution, and that turns out to be the conjugate prior there. You can look up formulas for it, and you can simulate it in R or Python without too much trouble. So that turns out to be the conjugate prior. And the main thing I wanted to notice from this is, so E of theta j given yj, so that's called the posterior mean. It's the expected value, or the average value, of theta j is the parameter you're interested in, which is the true kidney cancer death rate, which is unknown. And this is Bayesian, so it's given yj. So conditional on the data, what would you say about the average or expected value of this kidney cancer death rate? And notice it's, again, a weighted average. So like in the cases that we discussed before, the beta binomial and the normal, it's a weighted average of the prior mean. E of theta j is the prior mean. And then the data, so yj over 10 nj is just the naive estimate, just like how many people have kidney cancer divided by number of people, okay? So it's a weighted combination of those things. And the W is going to depend on, the weights are going to depend on how big is the sample size and how sure are you about the prior, okay? And in this example, in the Gelman book, they took an empirical Bayes approach. So again, the controversy for Bayes is like, where does the prior come from? Like, what's alpha and what's lambda? Those are the parameters of the gamma. But how do you choose those, okay? And so they did an empirical Bayes approach where they estimated those are called the hyperparameters, alpha and lambda. It's the parameters of the parameter, right? So they estimated those just using the overall entire data set. And then here's the raw data shown a different way. So the x-axis is population, actually the log base 10 of population. And so we're looking at population, and then on the vertical axis, we're looking at the death rate per 100,000 people. And what you see is that the small populations are accounting for most. If you look at the really high death rates, like the dots up high, and the really low ones, see all those ones at 0 or very close to 0, those almost all come from counties with very, very small population. So this is just a visual way to see that fact that we kind of discussed intuitively before, that a small county then is going to make up for a lot of or most of the cases of very high or very low. Okay, so that's kind of an intuitive observation that somehow we have to adjust for the sample size, but it doesn't say how do you actually do that adjustment. And for that we need a model, and natural choice is this Poisson gamma thing. Okay, so if we use that Poisson gamma model, then this was the result for these are the predicted values or the estimated values for the death rates after you do your Bayesian thing, right? That is, you're incorporating the prior information. And now you notice that there's much less variation. Like over here, it goes from like 0 to 25 as the death rate per 100,000. Here the scale is only from like 3 to 7, so it's much less variable, and you don't see the same thing where all the very large and very small values are coming from the small populations. Actually, for the small counties, they're just going to get pushed to the mean anyway, which is makes sense, because if it's a very small county, you simply do not have enough data, so your prior is going to be much more reliable. It could be that some county has some kind of environmental condition that causes kidney cancer, but you're just not going to be able to tell because it's such a small county and you just don't have enough data. So it's hard to get around that. Okay, and as I mentioned earlier, you know, the Bayesian machinery, it doesn't just give you point estimates, it lets you compute credible intervals, you can find posterior medians or whatever quantity you want, you just read it off of the posterior distribution. So this is a picture just showing 50% credible intervals for different counties grouped by population. And then the posterior medians, so that means, you know, you look at the posterior distribution and find the median. So half of the mass is to the right and half is to the left. That's a reasonable, you know, point estimate to use, and then intervals for each of them. So you can construct these kinds of things in a very natural way. All right, so I mentioned posterior median, and we mentioned posterior mean, and, you know, one of the biggest challenges in statistics is how do you actually decide what procedure to use, right? That's the big question. It's like, what should you do, okay? And you can come up with all these different things, right? You can come up with all these different tests and all these different procedures and all these different ways to estimate things. How do you decide? So we've talked about maximum likelihood and some other approaches to estimation, and maximum likelihood has various nice properties, but sometimes it's terrible. So, you know, how do you actually decide? Or you can come up with, you know, Bayesian methods. If you're approaching these problems like a Bayesian, you construct this posterior distribution, but let's suppose we just want to come up with one estimate or one prediction. How would you go from this entire curve and just do one estimate? You know, should you do the posterior mode? That is like look for the peak. A lot of people do that, right? They look at the posterior distribution, find the peak, and use that value. Do you use the mean, the median, the mode, or something else, okay? How do you actually decide what is good and what is bad? All right, those are really big, difficult questions. And one nice framework for thinking about those questions is what's called decision theory or decision analysis. As the name suggests, decision theory means you're trying to make a decision, okay? And so this is one, you know, foundational approach to statistics where some of the ideas come from game theory. Now, you think of it as you, the data scientist or statistician, are playing a game against nature, right? And nature has these secrets that you're trying to unlock, okay? So in this game theory setup, you imagine nature gets to play one move, and that move is just to choose a parameter value. And nature is nice enough to give you some data, right? And then what do you do with the data? Well, we're going to use the data to make some decision or take some action, okay? And this is a very general framework. So that action could mean that we're going to estimate a parameter. It could mean that we're going to try to predict a future observation. Could mean that we're going to decide whether to accept or reject a hypothesis. Could be that we need to provide an interval. You know, it's a very, very general setup. Okay, and then still, this doesn't yet answer the question of how do you decide what to do, right? So we're thinking of it as this game, nature versus data scientist. You have to decide what are the payoffs or outcomes of the game. So nature chooses the parameter, you choose an action, and then you get some loss that's based on a loss function that has to be specified, okay? And then you want to find procedures that will minimize your losses. That still doesn't tell us what to do, though, because just minimizing your loss, you know, the loss depends on what the parameter value is, but you don't know the parameter value is. Okay, so typically you can come up with all these different procedures for estimation or whatever you're doing, and you know, one procedure will work really well for one parameter value, but badly on another one, and then another procedure is like the other way around. So you somehow want one that's going to work well for most parameter values or for typical parameter values, that kind of thing. Okay, so here's the two most famous, widely used loss functions for estimation. First one is called L2, which is also just called mean squared error, and this one we have talked about a couple times. And that's just saying, on average, what's the square difference? So theta is the truth that we're trying to estimate, and we're using theta hat as our estimator of the truth. Okay, and then we say that the loss we incur is just the squared difference between the truth and our estimate. Okay, in some ways it's more natural to use absolute value instead, and there's nothing wrong with that. And in fact, when we look at the difference between ridge regression and lasso, it also gets at this L1 versus L2 thing, that in lasso imposes an L1 penalty, and this absolute values has these sharp corners, which helps give us sparsity in that case. But mean squared error, L2, is the most widely used loss function in general in statistics. And at least for continuous data. You might want to do something else for binary, when you're trying to predict yes or no. And that's mainly because of the nice geometry, and squaring is a nice differentiable function. It reminds you of the Pythagorean theorem and has a lot of nice geometry associated with it. Absolute value has this sharp corner, which can be annoying to deal with. All right, so these are the two most famous loss functions, but depending on the problem, the ideal would be not that you use one of these two. The ideal would be that your loss function represents actual losses. And it's going to cost you some amount of, which you could measure in dollars or something like that. And you actually, if you're off by this amount, how much is it actually going to cost you? Then you could actually come up with a real loss function. But if you just kind of want a default, typical one, these are the common default choices. All right, so if you're willing to take a Bayesian approach here and give theta some distribution, then you can say, well, let's look at, given the data, let's try to minimize our expected posterior loss. That is, we have the data, we construct the posterior distribution for theta, and then we say, on average, how far off are we if we use this procedure? And it turns out, it's not very hard to show, do a little calculation, that if your loss function is mean squared error, the optimal thing to do, it would be to use the posterior mean, okay? So we just, create these posterior distributions, which is really easy to do if you have a conjugate prior. If you don't have a conjugate prior, it's harder, but you can still often do the calculation. And then pick the mean of that distribution, okay? That turns out to be optimal. If you're using absolute error loss instead, then it turns out that the optimal thing to do is, again, take the posterior distribution and find the median, okay? So instead of having an abstract debate about is the mean better or the median better or the mode is better, this kind of says, let's see what loss functions it corresponds to. And you should first decide what your loss function is. Given the loss function, we can try to study which procedure works well for that. But if we haven't even specified the loss function, then, how do you even decide whether one thing is better than another? So it comes back to bias variance trade-off also. Mean squared error is the variance plus the squared bias. So there are these nice, if you're using mean squared error, it has a close connection with bias variance trade-off. But if that's not the loss function you want to use, then you'll still have bias variance trade-offs in some form, but it's not as direct a decomposition like that. Okay, so that's the decision theory, and this is a big subject. I'm only going to spend a few minutes on it, but I just wanted to show one kind of picture. This is just a completely made up case where suppose that there are only two possible parameter values. That is, theta is either equal to theta 1 or theta 2. Okay, so it's like that there's two possibilities, right? Either the hypothesis is true or it's false, rather than having a continuous thing. And then you can draw pictures like this. So I chose two possible values of theta just so that I can draw it in 2 dimensions, okay? If theta has 100 possible values, then you would have a 100-dimensional thing, which you can't visualize, or at least not easily. Okay, and these points, D1 through D8, correspond to different decision rules. And for example, D4 is like 5, 2 point something. What that means is if the true value of theta is theta 1, we're going to incur a loss around 5. And if the true value of the parameter is theta 2, then we're going to incur a loss of like 2 point something, okay? Or like D1, if the true parameter value is theta 1, our loss is going to be around 1. And if the true parameter value is theta 2, then our loss is going to be around 8, right? So for whatever procedure we're taking, we can find some point that it corresponds to that describes under both scenarios, so under both possible values of theta, how much loss will we incur. And actually, we used R here. It's actually risk, not loss. Risk is the expected loss. So it's saying that if the true parameter value is theta 1, the average loss will be whatever that value is. If the true value is theta 2, the average loss will be whatever the vertical value is. Okay? So you can kind of use this type of picture conceptually just to understand some of the key concepts and definitions in decision theory. For example, admissibility, which we already referred to. So in the James Stein problem, the MLE is inadmissible. And we saw that example where it's better to combine these independent problems into one estimator. In this picture, a procedure is inadmissible if you can find something that is to the southwest of it, right? Because if you can find one point, for example, D5 is inadmissible because both D3 and D4 are, downwards and to the left, right? So southwest. Both D3 and D4 lie to the southwest relative to D5, so they both dominate D5. Like, why would you use the procedure D5 when D3 is going to be better in all dimensions, okay, across all coordinates? So that's what admissibility means. And in this picture, all of those, any procedure that's on that blue line, the blue kinked line, piecewise linear thing, that frontier there, those are admissible. Everything upward and to the right of those is inadmissible because you can find one of these points like D1 through D6 that do better. Okay. All right, so I just wanted to get that concept. This is a way to picture what admissibility means. It means if you can do better across the board. All right, so one theorem. This is just the theorem of the day. This is called the complete class theorem. This is my favorite theorem in decision theory. It says that if you're applying a Bayesian procedure, it will automatically be admissible. So it will be one of those points on the frontier there, unless you have a dogmatic prior. So if your prior says you're 100% sure that theta is theta 1, that might not be admissible. But unless you have something that's ridiculously extreme, it will be admissible. That means, other procedures might be better some of the time, and nothing's going to beat it across the board. And the really surprising thing is the reverse direction of that, which says that any admissible procedure is Bayesian or possibly a limit of Bayesian procedures. Okay? So it says if you come up with, it's kind of an ironic theorem in the sense that it used to be, that there were these nasty controversies between Bayesians and frequentists, and there were the frequentists who rejected any kind of Bayesian thinking. And then someone proved this theorem, which says that if you want to be admissible, you have to be Bayesian. And, it doesn't mean that you have to be Bayesian it doesn't mean that you have to use Bayesian thinking to come up with your method, but what it does mean is if your method is admissible, it actually has some Bayesian interpretation. You may or may not know what that interpretation is, and you could choose whether you want to actually use Bayesian thinking to come up with your method. But there is some underlying Bayesian interpretation. Okay, so this again goes back to this Venn diagram that, you want methods that are good from both Bayesian and frequentist standpoints. And if you come up with a procedure from purely frequentist grounds that does not actually have a Bayesian interpretation, it will be inadmissible, which means you can beat it across the board in terms of the expected loss. And this is, holds under very, very general circumstances. All right. So last thing for today, I just wanted to give you, it's another huge subject. Decision theory is a huge subject. I just wanted to give you a super brief overview of what should you do if you want to use Bayesian methods, but your problem is more complicated. You can't just use conjugate priors. And actually, I want to mention one other extension first, which is, okay, so suppose you can't just do the simple conjugate thing like the beta binomial and the normal. A lot of times you can still, so if you're dealing with a continuous problem and you write down Bayes' rule, and you have this, it says that the posterior is proportional to the likelihood times the prior. And it's really, really useful that it's proportional, and a lot of times you don't actually need the denominator. Sometimes, though, you do, like let's say you want to compute the posterior mean, but suppose you don't know how to do it, you don't know how to do all the math. A lot of times you can just discretize the problem and kind of construct a grid, even if you're working with a continuous thing, and just make it something discrete and break up the problem, like theta might be a continuous parameter, and I'm just going to say, well, I'm going to assume theta is between 0 and 100, and I'm going to go 0, make a grid with spacings like 0.001, and just do the discrete version of Bayes' rule, and Bayes' rule is a very simple formula, right? And you can just calculate it. And so you can just discretize Bayes' rule. And basically that's just saying approximate. In general, in the continuous case, you get these integrals, and often the integrals are really hard to do. But a lot of times you can just approximate it as a sum without too much difficulty. Okay. Now suppose you have a harder problem, where you're just working with this vast space and you have completely intractable. So if you wanted to calculate, the posterior distribution results explicitly, you would have to do some intractable sums or intractable integrals. Like let's say it would involve a sum of 2 to the 1,000 terms or something like that. A very powerful method for dealing with those problems is what's called Markov chain Monte Carlo. This is an example from Percy Diaconis and Mark Coram. Percy was my advisor at Stanford. And, it's a huge subject, so I'm just going to give you one or two quick examples or ideas, and it's a topic that's covered in depth in other courses. But I just want you to at least be familiar with the concepts so that if you need it, you know where to look for more. MCMC, Markov chain Monte Carlo, is really what probably the biggest driving factor in the rise of, and growth in Bayesian applications in practice, because it greatly increased the range of different models for which you can apply Bayesian approaches successfully. The idea is that I'm not actually assuming you know what a Markov chain is. Just in brief, just think of something like a random walk. And I'm not going to go through the formal definitions of it because it's not the topic of this course. But just imagine something where you're jumping from state to state and you don't care about the whole past history of how you got to the current state. All that matters for predicting the future is what your current state is. So it's a famous model in stochastic processes, which would be courses like Stat 171, where you have random variables evolving over time. And, when you're working with stochastic processes, you're try to model the world using these random processes. You can always wonder, when you have something like the Markov assumption. So the Markov assumption says, given the present, the past and future are conditionally independent. So for a real, data set, and you're wondering whether it's Markov or not, that's a hard empirical question. The idea of MCMC is that you create your own Markov chain. Okay, so there's no question about whether it's a Markov chain or not. You construct your own. And you design your own Markov chain whose stationary distribution is the limiting distribution. So if you run the Markov chain for a long time, what's the distribution going to look like? That's called the stationary distribution. The idea of MCMC is that you create your own Markov chain that, in the long run, that chain will converge to the posterior distribution you're interested in. So the idea is you construct this chain, and then you just run the chain for a long time, and it's simulating draws for you from the posterior distribution of interest, which is really, really nice, because then if you're interested in, for example, the posterior mean, of some parameter, I'm just going to run this Markov chain for a long time, and then I'm just going to average the values, and then, I'll use that, right? So it's a simulation-based way to compute a posterior distribution rather than having to do horrible, intractable sums and integrals. Okay, so just one example of that for today. This is an example that Diaconis and Coram were working with a prison code that someone brought to their attention that they wanted help. This was something that was written in a prison, and the people who found it had no idea how do you decode this, right? It seemed to be, a variety of different symbols. What does this actually mean? Okay, well, you could bring this to a cryptography expert, and, there's basic, methods like based on frequencies in English, and this actually gets us into text analysis, which is something we'll be talking about next time. You could download a big database of books or materials written in English and then look at the frequencies of different letters, right? So in English, E is the most common letter by far, okay? So you could kind of categorize, what are the symbols here, and then you could get, assuming that this was originally written in English or maybe Spanish, which also has a lot of E's, and then you could look for, which symbol appears the most and try to guess that that's an E, and then look at the second most frequent letter in English, and then second most frequent symbol in here, and so on. And you could try to do that. That would work for some very simple types of ciphers where you're just replacing one letter with one symbol. Okay, but suppose that you didn't actually, well, that's not even going to work so well that maybe you get the E right. But think about it this way. Even assuming that that's, what it looks like is just a simple cipher like that, there's 26 factorial, suppose there's 26 symbols here and 26 letters from A to Z. There's 26 factorial different permutations. So 26 factorial ways to match those things up. So anyway, they came out with an MCMC-based method to try to break the code without having to actually know much about cryptography and without having to do a lot of work and trying different things. So what they did was that they created a transition matrix. So this is just based on, so if I just looked at which letter is the most common and second most common and so on, that doesn't take into account any of the transitions from one letter to another, right? Like in English, Q is almost always followed by U. Okay, so if you notice that, certain pairs that one letter, one symbol almost always followed by another, you might guess that's the QU, pattern, that kind of thing. Okay, so, they downloaded some text in English to estimate these transition probabilities. And then they defined this thing called plausibility. So F is a specific, possible candidate for what the code is, right? So F is one of the 26 factorial ways to match up letters in English with symbols in the prison code. And then they define the plausibility to just be the product of these, M of F of Si, F of Si, I plus 1. That's just saying, look at, assuming that is the truth, right? If F is the true way to decode this, then I'm going, let's say take a word like statistics. I go from S to T and T to A and all these transitions and just multiply the probabilities of those transitions. So the idea is that if we get the right permutation, then the plausibility is going to be pretty high because we have transitions that are very common, like Q followed by U and T is often followed by E and things like that, right? Whereas if we get the permutation wrong, then there's going to be lots of very, very unlikely transitions, right? Like you don't have a lot of words in English that go like Z followed by, W followed by Z or something like that. That would be very rare. So, okay. So, doing that, and then to test it out, they took, some lines from Hamlet and then started with, so that was assuming that this is what they actually want to get, they want to recover for the simulation purposes, recover some lines from Hamlet, what do? Well, and then you just start out with a random encoding, and then just run this thing. And after like 2,000 steps, it's already doing really well, which is kind of surprising because 26 factorial is a ridiculously large number. So I didn't describe the details of their algorithm. What their algorithm is doing, it defines these plausibilities, and then it defines a Markov chain as follows. So start with one permutation, right? So one possible way to match up letters with symbols. And you try it out, and you compute the plausibility. And then you pick randomly two of the letters. Let's say I pick C and G. And I swap what C and G are paired up with, right? So maybe C is matched with one symbol, G is matched with another, and with some probability, I swap them, okay? And there are clever ways that we'll talk a little bit about next time for deciding, for figuring out what's the probability that you should do that swap, okay? But that's the basic idea is that we're using a Markov chain to explore a space. The space we're exploring is the space of all possible codes, which is 26 factorial. It's a ridiculously large number, okay? And the way we explore that space is pick two random letters and then swap how we decoded those letters. And intuitively, it seems like that's going to, be very hard to explore the space there. But actually, in this example and a lot of other examples, it actually works really well. And after a few thousand steps, not after billions of steps, after a few thousand steps, you actually converge to something good. So I'm going to stop here because we're out of time. So thanks.